Okay, now we're going to look at advanced language constructs, and we're going to look at patterns and past operators. So patterns, they are ways to group different constraints and even have some kind of private variables defined. So a pattern is usually defined in with its own name. Then it has different parameters. This can be expressions that evaluate to Boolean values, and then we can define internal variables of a pattern that they can keep, then some where they can keep, for example, a state of something. So they could monitor some state and decide what to do based on this state monitoring that they do, but they are much more powerful than just state monitoring because they can have initial safety and liveness constraints inside patterns. So you can do very powerful things with patterns, and we showed that you can do quite powerful things. For example, yeah, the combination of these LTL operators, and you can express them into patterns, and we've done this automatically for some patterns, so they are quite complicated LTL formulas that you are able to express into these GR1 patterns just with the usual GR1 constructs. And the patterns that we see here in this pattern catalog, they are taken from Dwyer patterns, so they are known as the LTL specification patterns. And most of them are supported in Spectra through this pattern mechanism. But you can also define your own patterns. So yeah, this is the way you define patterns, and then of course we would like to instantiate them. So there's a very interesting pattern here, the response pattern, S responds to P. So we might want to use that pattern and instantiate it for our traffic light example. So in our traffic light example, we might want to say, we might want to have a guarantee that S responds to P. The two parameters are, first parameter is P. So if we have a car in lane A, then we want to respond to it with a green light on B. And now this response is not necessarily an immediate response. So what can happen is that this response will only happen after a few more steps. And this is very powerful because this allows us to simply instantiate this into a single line that we say, well, after sometime after this happened, after there's a car on A, we guarantee that there will be a green light on A. And we can do the same for B, of course, that after there was a car on B, we guarantee that after some finite time, always when there's a car on B, after some finite time, there'll be a green light on B. And if we check now if this is still realizable, yep, it is, and it can give us a controller. And this controller is a bit more complex than it was before, but this is because it keeps track of whether there is the need to turn the green light on each of the streets, and it has to keep track of this because it can't turn them on at the same time. So there are some other patterns here. So maybe in our grid world, we have now some positions defined, basically the corners, corner 0, 0, then another corner and another corner with these positions. And we might want to say that we want the robot to always return to this corner 0 in between visiting this position P2 and P3. So there is another pattern for this. Let's see. There is, for example, this P becomes true between Q and R pattern. So let's try to instantiate this here. We would have we instantiate it again as a guarantee, but you could also instantiate patterns as assumptions. The important thing is you don't use any temporal operators because the patterns have temporal operators inside. And yeah, then P becomes true. So let's have P1. We want it to be true between visiting this P2 and P3. And now if we synthesize a controller for this, then let's first check realizability. It is realizable. And if we synthesize a controller for this, then this controller would visit P2 and P3 and always make sure that it visits P1 in between. So yeah, it's a little bit too large to look at now, but yeah, you can try it on a smaller grid maybe. Okay, so this is the patterns. Now there's also another thing called past operators. I mean, in Spectra we have the temporal operators that we saw previously. We have ini that just relates to the initial state. We have always that relates to any state, and then we have always eventually that relates to infinitely many states in the future. And there are also other temporal operators, for example, previous or historically or once, and these are past operators. They relate to some point in the past. So if we wanted to write a guarantee that always, or maybe an assumption that always eventually once, we can write once like this. There was a car at A, then this would be the assumption that at some point in the future, if we look at the past, there was once a car on lane A. So this once, the past operators, they are described in the user guide. You can write once typed out, or you can just write O. So maybe let's just have it fully typed out. And then there are also other operators like historically, so we could even nest them, which we can't do with the other temporal operators in Spectra, but past operators we can nest. So this means that once historically, so historically refers to from the current point of time back to the beginning of time. But now this is in the context of once. So this means that there's some period at the beginning of every run of this system where car A was true. Okay, and then you can also do other things where you could, for example, have another operator called previous. So we might have a guarantee that always, if we have green A, this implies previous green B. Something like this you could write with past LTL operators. Okay, and the simple task for this would be extending the specification of the traffic light with a pattern in an assumption. So patterns in assumptions, they are just the same as patterns in guarantees. You just put in the pattern in assumption instead of guarantee and instantiate it the same way. So here we need to add an assumption that car A is always eventually followed by car B, and you can do that with the response pattern. Let's just have a quick look back. So we use the Dwyer patterns and we have to import them. So if you want to use them in a specification, you need to copy the Dwyer patterns catalog and into some directory that is reachable from your specification. So you can also use ... and path navigation, but this way you can import collections of patterns, for example.